Hello everyone, welcome to this channel. Today we are going to see crystal field theory and splitting of octahedral and tetrahedral complexes. Valence bond theory tells about bonding in complexes, but it has some limitations. Then crystal field theory is used to explain the properties such as color, magnetic behavior, etc. However, this theory was originally used to explain the nature of bonding in ionic crystals, but later on it is used to explain the properties of transition metals and their complexes. Some of the important features of crystal field theory are: these are the important points in crystal field theory. That is, crystal field theory assumes that the bond between ligand and central metal atom is purely ionic. This is the first point. And the second point is, in coordination compounds, the central metal ion and ligand are considered as point charges or electric dipoles. Second point is, the central metal ion or ligand is considered as point charges or electric dipoles. Then the third point is, the complex formation is considered as the following series of hypothetical steps. That is, the complex formation is considered by using this series of hypothetical steps. See, these two steps are very easy. In step 1, the ligands form a spherical field of negative charge around the central metal ion. In step 1, the ligands are present around the central metal ion, and in the step 2, the ligands approach the central metal ion in all the direction as shown in the diagram. You can see the ligands approaching the metal ion in all the direction in step 2. This is said in step 2. To briefly explain step 1, what they say is, in an isolated gaseous state, all the D orbitals remain degenerate. No splitting takes place in the isolated gaseous state, which is said in step 1. Then, in step 2, the ligands approach the central metal ion in all the direction. So, to illustrate this, let us consider an octahedral field in which central metal ion is located at the origin and 6 ligands are coming from this direction. What is in the diagram? They are illustrating. They are illustrating here. That's all, very simple. See, the orbitals lying along the axis will have greater repulsion than the orbitals lying in between the axis. That is, dx square minus y square and dz square orbital lie along the axis, and dxy, dyz and dzx orbital lie in between the axis. This is in the case of octahedral complexes that we can see from the diagram. Thus, the degenerate d orbitals split into two sets, and the process is called crystal field splitting. That is, in crystal field splitting, the degenerate d orbital will split into T2g and Eg orbitals. That is, we can see in the case of octahedral and tetrahedral complexes. See, this d orbital split into T2g and Eg. Then dx square and dx square minus y square and dz square lie along the axis, and dxy, dyz and dxz lie in between the axis. Okay. Then step 3. Up to this point, there is no complex formation. Till now, there is no complex formation, but when the ligand approach further, when the ligand approach closer, there will be attraction between negatively charged electron and positively charged metal ion. This results in decrease in energy. This decrease in energy leads to complex formation. This is a simple step. Just understanding is necessary. Then crystal field splitting in octahedral complexes. This we can explain from this diagram itself. Just we have to understand this diagram and frame the sentence. What they say is, the energy of dx square minus y square and dz square. Dx square minus y square and dz square orbital is represented as Eg, and dxy, yz and dxz orbital is represented as T2g. The energy of Eg orbital is higher in case of octahedral complex than T2g orbital. See, Eg orbital will have higher energy. We have to represent the arrow like this, whereas T2g orbital will have lower energy. Like this, we have to represent the arrow downwards, so it has lower energy. Then the increase in energy is represented by 3 by 5. How we are considering this 3 by 5? This I am going to explain. Wait. We have 3 orbitals dxy. Out of 5 orbitals, we have 3 xy, yz and zx on the opposite side. So we have to put 3 here. Since the arrow is pointing upwards, we have increase in energy. So we have to put positive charge. On the opposite side, we have 3 orbitals out of 5 orbitals. So 3 by 5. So plus 3 by 5 delta naught. Then minus 2 by 5. How we assume this is? The minus sign is due to this arrow is decreasing. So we have to put minus sign. Minus. How this 2 by 5 is coming? See, we have 5 d orbitals. So this 5. Then on the opposite side, we have 2 Eg orbitals. So we have to put 2 on the top. So it is represented by minus 2 by 5 delta naught. Then the next thing is this delta naught. This delta naught is the crystal field splitting energy. Crystal field splitting in tetrahedral complexes. See, these are very big paragraph. Just reading this paragraph is enough. I will say what is the important points in this paragraph. Okay. First, what they are saying is the approach of ligand in tetrahedral field can be visualized from this diagram. See this diagram. In this we can see the approach of ligand in tetrahedral field. These are the ligands. Ligand 2 and ligand 1. These are the ligands. Then consider a cube in which the central metal ion is placed at the center. The 4 ligands approach the central metal atom along the direction. See, this is the central metal ion. The ligands, 4 ligands. Since it is a tetrahedral complex, there will be 4 ligands. See, these are the ligands L1, L2, L3 and L4. These ligands approach the central metal atom, which is said in these slides. Then coming to the next para, none of the d orbital point directly towards the ligand. However, T2 orbital are pointing close to the direction in which ligands are approaching than the E orbitals. What they say is T2 orbitals are closer when compared to the E orbitals. That's it. You can see in this diagram T2 orbitals d, y, z, dxz and dxy. Then E orbital dz square, dx square minus y square. That's it. Then this para you should understand from the splitting of d orbitals. By understanding the splitting of d orbitals, we can write this para. See, this is the diagram of splitting of d orbital in a tetrahedral field. See, this splitting is more important in octahedral and tetrahedral. So this splitting is very, very important, and we can easily understand the splitting. That is the d orbital. If d orbital split into T2 and E in tetrahedral complex. See, where T2 is in higher energy and E is in lower energy. Opposite of octahedral complex. In octahedral complex, Eg will have higher energy, T2G will have lower energy. Whereas in tetrahedral complex, T2 is present in higher energy and E is present in lower energy. The same, in T2 we have dxy, dyz and dxz orbital, and in EG we have dx square minus y square and dz square orbital. So T2 will have increase in energy and V we have decrease in energy. So plus 2 by 5. 2 by 5 delta T and minus 3 by 5 delta T. How this comes means we have to, because on the opposite side we have two orbitals dx square minus y square and dz square. Out of 5 orbitals we have 2 orbitals in the opposite side, so we have 2 on the top, that is plus 2 by 5 delta T. Then minus 3 by 5, this minus symbol indicates the decrease in energy. There will be a decrease in energy, that is the arrow is in the reverse direction, so minus denotes the decrease in energy. This 3 comes from, that is on the opposite side we have 3 orbitals dxy, dyz and dxz. Out of 5 orbitals we have 3 orbitals in the opposite side. So this 3 by 5 comes from this. So minus 3 by 5 delta T. So the relation between delta T and delta naught is, delta T means tetrahedral complex. T represents tetrahedral complex. Delta T is equal to 4 by 9 delta naught. This gives the relationship between delta T and delta naught is given by delta T is equal to 4 by 9 delta naught.